Okay. So yeah, let's till last class, what we were doing is we were looking into some concepts with regards to the design of reactors and reaction kinetics. We looked into some derivations for second order reactions and reversible reactions. So today also we'll look into some more concepts for okay. So today also we'll be looking into a few more concepts. Uh, we'll look into a concept called half-life of a reaction, and we'll look into series or parallel reactions. We'll like briefly look into the equations for series and parallel reactions, and if possible, we'll also look into some more terms called as selectivity and yield. Okay, fine. So after this, we'll get on to solve like few problems with regards to these concepts from previous year gate questions. So let us start. The first thing that we look into today is half-life. So a half-life of a reactor is nothing but the time required for the reaction to reach 50% conversion. So let's say we have a reaction A gives B, and let's say the initial concentration of A Ca0 is let's say 10 mole per liter. The time required for this reaction to reach a point where the concentration of A will become 5 mole per liter. That means the conversion is 50%. So this is what is known as half-life of a reaction. So basically at half-life, we usually represent the time required for half-life is T half. So at half-life, the final conversion Ca is basically Ca0 by 2. And we can apply this equation in our general equation. So let's say for nth order, we have the equation n minus 1 kt is equal to 1 by Ca raised to n minus 1 minus 1 by Ca0 raised to n minus 1. So what we can do is we can substitute this Ca raised to n minus 1 as Ca0 by 2 the whole raised to n minus 1. And we can do a bit of rearrangement in this equation, and we can get an equation for T half. So for T half, and when we substitute this Ca as Ca0 by 2, then T will become T half, right? So then we can write T half as Ca0 raised to 1 minus n, 1 minus 0.5 raised to 1 minus n by k into 1 minus n. So this is the general equation for half-life. Okay, so let's see how for each reaction's order this half-life changes. So let's say we are taking 0 order. At 0 order, n is equal to 0. So our general equation T half is equal to Ca0 raised to 1 minus n, 1 minus 0.5 raised to 1 minus n by k into 1 minus n. So we just have to substitute all these n's as zeros and we'll get t half is equal to Ca0 raised to 1, and just substitute all the n's as zeros and we'll get Ca0 by 2k. So this is the half-life for a zero order reaction. And let's say if we want to find t half for a first order reaction, this is for first order reaction, this will somewhat differ. Okay, so for first order n is equal to 1. So in all these exponential terms in the general equation, we see that it is 1 minus n, and if we substitute n as 1, it will be 1 minus 1, that will be 0, and this equation will not make sense. So for first order reaction, what we have to do is we have to take the general equation for first order reaction. So the general equation is basically ln Ca by Ca0 is equal to kT. So how we got this equation? Just by the normal derivation. For first order, it's dCa by dt is equal to kCa. And if we integrate this term, we will get the general equation for the first order, which is ln Ca by Ca0 is equal to kT. Now all we have to do is just substitute Ca as Ca0 by 2. So that means this equation for first order will become ln Ca0 by 2 and Ca0 is equal to kT. That means ln 0.5 is equal to kT. KT half. Okay. Because we are finding half-life. So basically T half for a first order will be ln 0.5 by k. And this is nothing but 0.693 by k. The T half for first order. So similarly, we can do for various orders as well. We'll do second order and then we'll stop there. So let's say for second order, n is equal to 2. The general equation for second order is 1 by Ca minus 1 by Ca0 is equal to kT. And at T half, this will become 1 by Ca0 by 2 minus 1 by Ca0 is equal to k T half. Right? Yeah. And all we have to do is just rearrange this, and finally we'll get T half is equal to 1 by k Ca0. Right. So we can keep doing this for third order or even higher orders and so on. So basically this is what we mean by half-life. So again, half-life is nothing but the time required for the reaction to reach 50% of its completion or reach 50% of its 50% of the conversion. So the conversion will be 50% of the reactant, right? Okay. Let's move on to the next topic, series and parallel reactions. So we'll start with the series reaction. Just a second. So yeah, let's move on to series reactions. Let's take a reaction. Let's say A gives, R gives S. So this is a series reaction. So I hope you guys know the terms series and parallel. So series means things will be happening side by side. For example, this reaction. First, the reaction A gives R happens, and or side simultaneously R will also give S, and this all will happen in a series. So, and let's say K1 and K2 are the rate constants for these series reactions. So we can write three equations for rate. The first equation is rate of disappearance of A. So that is minus Ra, and that will be K1 Ca, where Ca is the concentration of A. Now we can also write this in terms of rate of formation of R. So let's say RR. This will be K1 Ca minus K2 Cr. How this two terms came to be for this rate equation is that there are two reactions for R. First, the reaction of R being formed from A, right? So R is first forming from the reaction from A, and simultaneously R is also disappearing through the reaction R gives S. So the rate equation will be K1 Ca, which represents the rate of formation of R, minus K2 Cr, which represents the rate of disappearance of R. Okay, so this is one, and obviously we can write one equation for S as well. So rate of formation of S, and that depends only on the concentration of Cr, and that will be K2 Cr. Okay, so we usually use this uh, reaction rate, and we'll use this equation to derive a general term for such reactions. So let's see. This RR, this is basically dCr by dt, that is equal to K1 Ca minus K2 Cr, right? So here also, here one assumption is that all these reactions are first order. Okay, so all these series reaction that happens here are first order. Right. So the first order, terms are applicable here. So one of the terms, let's say, where is it? Yeah. So minus Ra is equal to dCa by dt is equal to K1 Ca. And from this we can get the first order term as Ca is equal to Ca0 e raised to minus kt, or it just last slide we saw, this is basically ln Ca by Ca0, which is minus kt. So these things you can use it here as well. So it's a huge integration here. So basically what we have to do is we have to integrate this um, equation. dCr by dt is equal to K1 Ca minus K2 Cr, and we can substitute Ca as Ca0 into e raised to minus kt. We can even uh, write this like this: dCr by dt plus K2Cr is equal to K1 Ca. So this is a non-linear equation. So this is like of the form dy by dt plus py is equal to q. Okay, and you might have learned this integration of such terms, we integrated using integrating factors. So I'm not gonna do this integration here, but basically this is just the concept of this integration. So we use integrating factors and we integrate this equation, and finally we'll try to write the terms of concentration of A, R, and S using this integration. So basically, if you integrate this, what we can find is, I'll just write the general expressions here. We can find an expression for CR as K1 CA0 by K2 minus K1 whole into e raised to minus K1T minus e raised to minus K2T. Right? And we can write an equation for CS as well. So CS is basically nothing but CA0 minus CA minus CR. Okay, so I'll write this again in the next page. So first, we have A gives R gives S. If you want to find the concentration of A, CA is nothing but CA0 into e raised to minus KT. And CR we just found out as K1 CA0 by K2 minus K1 e raised to minus K1T minus e raised to minus K2T. Right. And CS, we can either find it as CA0 minus CA minus CR, or we can write an expression for this as well as, CA0 the whole into 1 minus e raised to minus K1T minus K1 by K2 minus K1 e raised to minus K1T minus e raised to minus K2T. Okay. So these three terms we found by integrating one of the rate equations, like here. So we integrated this second equation, the rate of R, and we found out these terms for concentration of different uh, reactants as well as the products, or basically the concentration of A, R, and S. Okay. Now let's take this these three concentration terms and let us try to plot it. Okay, so we are plotting it with respect to time and concentration, it's CA, CR, and CS. If we plot it, initially A is our only reactant, and A will be high initially, and it will start from here and it will go like this. A will decrease as the reaction proceeds or as the time progresses. R will have a profile like this. Initially R is 0. It will increase to a maximum and then it will start decreasing like this. Okay, so this is CA and this is CR. And similarly, S will also have a profile like this. CS. So again, just to keep note, these expressions that we have written here are under the assumption that these are first order series reactions. So let's say if you have a second order or third order reactions in series, you will have to use those terms, and you'll have to find the equations for the concentrations of A, R, and S. So yeah, so these three we have the profile for CA, CR, and CS. Now we'll define a term called optimum time. or T optimum. The time or the optimum time is nothing but the time at which concentration of R is maximum. So this is T optimum. Okay. So at T optimum or optimum time, the concentration of RCR is CR maximum. And because of this, rate of R will become 0. Okay. So using this term, so this is basically, dCr by dt. So dCr by dt will be 0. And using this, we can find an expression for T optimum as ln k2 by k1 by k2 minus k1. So this is the expression for T optimum or optimum time for a series reaction. And using this, we can also derive one relation between CR and CA0. So at T optimum, CR will be CR max, and by CA0, this will be equal to K1 by K2, the whole raised to K2 by K2 minus K1. So you will get these two equations by substituting these values. dCr by dt is equal to 0 at T is equal to T optimum, right? So that is about series reactions. And one more reaction we'll see, parallel reactions. So parallel reactions, in series reactions, reaction happens in series, like in an order. Parallel reactions happen simultaneously. So let's say A gives R, and simultaneously A will also give S. Okay, we can represent this as A simultaneously giving R and S. So these are our parallel reactions. These are like simple parallel reactions, and let's say they are first order reactions as well, with reaction rate constants K1 and K2. K1, K2. Right. So here also we can write the rate. So can anyone say what will be the rate of disappearance of A here? Like how or at least like how many terms will be here for rate of disappearance of A? Yeah. So the first term will depend on the first reaction A gives R, and the second term with regards to the second reaction A gives S. So basically what happens here is this rate of disappearance of A is nothing but K1 Ca plus K2 Cs. Okay, or we can even join this and write it as K1 plus K2. Oh, sorry, this is Ca. Okay, K2 Ca. K1 plus K2 Ca. Okay, so yeah, and let's say the rate of formation of R will be K1 Ca, and rate of formation of Rs will be K2 Ca. Now again, similar to what we did in the previous series and parallel reaction, we can also take this term for RR, which is dCr by dt as K1 Ca, and we can integrate this. How we'll integrate this, we'll see. So as I said, these are all first order reactions, right? So what we can do is take the rate of disappearance of A minus dCA by dt is equal to K1 plus K2 into Ca, and if we integrate this, we'll get ln Ca by Ca0 is equal to e raised to plus K2 into T, right? Or if we like rearrange this, we'll get Ca, sorry, e raised to minus Kt, right? Yeah. So, or if we rearrange this, we'll get Ca will be Ca0 e raised to minus K1 plus K2 into T. We'll substitute this Ca here. So dCr by dt will be K1 Ca0 e raised to minus of K1 plus K2 into T. Okay, so this is the differential equation with respect to the concentration Cr. And same as last time, we'll have to do some integration here. And finally, we'll get Cr as K1 Ca0 by K1 plus K2 1 minus e raised to minus K1 plus K2 into T. And Cs will be nothing but the same thing, but K2. So K2 Ca0 by K1 plus K2 into 1 minus e raised to minus K1 plus K2 to T. So these will be the equations for Cr and Cs, and this will be the equation for Ca. So we have the so similar to the last case, we found equations for the concentration of A, R and S. And similarly, like just like last time, what we'll do, we'll plot. So we can plot the concentrations as well as time. So this is time t and this is concentrations Ca, Cr and Cs. So similar to the last case, A will be highest during the initial stages and it will decrease as we proceed with the reaction. Okay. Now R and S will be 0 at time t equal to 0. So it will start from 0 and R will go like this, and this is Ca, this is Cr, and similar to this S will also go like this, Cs. Now whichever comes on top, this can even be Cs and this can be Cr. So whether this Cr or Cs, whichever comes on top, depends on the reaction rate constant of this R and S. So we had two reactions, right? A gives R and A gives S. So we had two reactions, K1 and K2, reaction rate constants. So the figure here where R is higher, the concentration of R is higher compared to concentration of S, here basically what we mean is K1 is greater than K2. Okay. Now let's say, K, sorry, let's say K2 is greater than K1. In that case, what happens is, this will be A this will be CS and this will be CR, because the reaction rate constants corresponding to the reaction that gives S is higher here. So that means the concentration of S will be higher compared to R. And one more case, if K1 is equal to K2, then the concentrations of R and S will overlap each other. So CR, CS. Because both their reaction rate constants are same, that means their rate of formation is also same, and their concentrations will also be same for the time, right? So yeah, so these are some things, some information regarding parallel reactions. Okay, fine. Any doubts so far? So if this is clear, we'll move on to solving some problems. So shall we move on to problems? Harshal? Harshal, am I audible? Okay, fine. Okay. So yeah, let's move on to these previous year gate questions. Okay. So this is a question from GATE 2016 from Chemical Engineering, question number 15. The variations of concentrations Ca, Cr, Cs for three species A, R, S with time in an isothermal homogeneous batch reactor are shown in the figure below. Select the reaction scheme that correctly represents the above plot. The numbers in the reaction schemes shown below represent the first order rate constants in the unit of second inverse. So this concentration profile is given on the side here. The concentration versus time profile of A, R, and S, and the four options given here are as below. So this is a question from parallel reactions part in chemical reaction engineering, and the reference can be found in module 1 lecture 33 multiple reactions part 2 chemical reaction engineering 1 homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So from the concentration profile we can we can see that the reaction is a parallel reaction, and from the options also we can understand that the reaction given here is parallel reaction. So for parallel reaction, the concentration profiles are as like this. So this will be the concentration profile Ca for, let's say, parallel reaction A gives R and A gives S. Okay, and the concentration profiles of Ca and Cr and Cs will be like this. Now the peculiar case is that firstly we need to note that the reactions, the parallel reactions here are irreversible reaction, and secondly in the given plot the profiles for Ca, sorry, Cr and Cs overlap each other. That means the concentrations of Cr and Cs are same at all times. This basically means the rate constant corresponding to R and the rate constant corresponding to S are also same. So we need to look for a parallel reaction which is irreversible, and also the reaction rate constants for R and S as same. So in these four options, that is true only for option C, because the reactions are irreversible here, as well as the reaction rate constants are same. Both the reaction rate constants are 1 and 1. So here the right option is option C. Yeah, yeah, Harshal, that was right actually. Your answer was right. So basically, I just gave you the explanation just once more. We just looked into this case just a few slides ago as well. So option C here is the right answer. Fine. Let's move on to the next question. This is a question. Yeah. So this is a question from GATE 2016 from Chemical Engineering, question number 16. Hydrogen iodide decomposes through the reaction 2Hi reversibly gives H2 plus I2. The value of universal gas constant R is 8.314 Joule per kilomole per Kelvin. The activation energy for the forward reaction is 184,000 Joule per mole. The ratio rounded off to the first decimal place of the forward reaction rate at 600 Kelvin to that at 550 Kelvin is dash. So this is a question from reaction kinetics part of chemical reaction engineering, and the reference can be found in module 2 lecture 3 kinetic model and temperature dependency, chemical reaction engineering 1 by Professor B. Mandal, Department of Chemical Engineering, IIT Guwahati. So in this question, they have given us a reaction which includes the formation of hydrogen and iodine from hydrogen iodide. So the reaction is 2Hi reversibly gives H2 plus I2. Now they have given us that we need to find the ratio of forward reaction. Let's say K1 is the forward reaction and K2 is the backward reaction. What we need to find here is the ratio of K1 and K2. We can find this by using Arrhenius theory. And by Arrhenius theory, K1 by K2 is nothing but exponential So by Arrhenius theory, one second. Yeah. So by Arrhenius theory, K is equal to K0 e raised to minus E by RT. Right. And if we take K1 as K10 e raised to minus E by RT1 and K2 as K20 e raised to minus e by r T2. If we take the ln, if we can divide this, and we'll get k1 by k2 as e raised to or exponential minus e by r into 1 by t1 minus 1 by minus 1 by t2. So we can find the ratio of the forward reaction to the backward reaction using this relation. And this relation we derived using Arrhenius equation. So here the forward reaction happens at T1, which is 600 Kelvin, and the backward reaction happens at T2, which is 550 Kelvin. The activation energy is given as E is equal to 184,000 joule per mole, and the universal gas constant R is given as 8.314 joule per mole Kelvin. So all we have to do is substitute these values of E, R, T1 and T2 in this equation, and we can find the ratio K1 by K2, which is the ratio of the forward reaction rate constant to that of backward reaction rate constant. Okay. So let us substitute it. K1 by K2 is equal to exponential of minus E by R 1 by T1 minus 1 by T2, and this will be exponential of minus 184,000 by 8.314 to 1 by 600 minus 1 by 550. So this is K1 by K2. And if we solve this, we'll get K1 by K2 as 28.6. Yeah, so Harshal said 0.48. Okay. Just recheck your calculations, or maybe there is some problem with the unit. If you want, we can try doing it as well. Let us see. That's the calculator. Can you recheck your calculation, Harshal? I'll also recheck the calculation from my side. Yeah, it is. For me, I'm getting 28.6 as the answer. Okay, that is fine. Just redo this calculation after the class and see if you are getting this answer. So I'm getting somewhere around 28.589, something like that. So The answer is I get is 28.6, and I think this is the answer that I found in the key as well, the answer key. So yeah. So yeah, as you just saw, this is basically a straightforward application of our Arrhenius equation. So all we have to do is just write the reaction rate constants in terms of Arrhenius theory, and just divide those two, and just substitute all these values, and finally you will get the final answer as 28.6, right? Yeah. The answer, I checked the calculation again and I'm getting the same answer, 28.6. So if you guys can do this calculation again, like after the class, just let me know, and we'll revisit this question. Okay, fine. Let's move on to the next question. So this is okay. So this is a question from GATE 2016 from chemical engineering. Oh, yes. One second. Okay. The screen visible now? Yeah. Okay. So this is a question from GATE 2016 from chemical engineering, question number 47. The liquid phase reversible reaction A reversibly giving B is carried out in an isothermal CSTR operating under steady state conditions. The inlet stream does not contain B and the concentration of A in the inlet stream is 10 mole per liter. The concentration of A at the reactor exit for residence times 1 second and 5 seconds are 8 mole per liter and 5 mole per liter respectively. Assume the forward and backward reactions are elementary following first order rate law. Also assume that the system has constant molar density. The rate constant of the forward reaction rate in second inverse rounded off to the third decimal place is dash. So this is a question from design of ideal reactors from chemical reaction engineering, and the reference NPTEL series can be found in module 1 lecture 17, design of mixed flow reactors, chemical reaction engineering 1, homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here in this question, a reactor or reaction A reversibly giving B is carried out in two different cases. So case 1, the residence time tau is 1 second, and case 2, the residence time tau is 5 seconds. So in case 1, the final concentration of Ca is given as 8 mole per liter, and in the case 2, for a residence time of 5 seconds, the concentration of Ca is given as 5 mole per liter. Right. So residence time here basically means the space time. So we can directly solve this question by using the design equation for CSTR. So for CSTR, we have the design equation tau is equal to Ca0 minus Ca by minus Ra. So this is the design equation for CSTR. Now what we'll do here is we'll do this design equation for both the cases. So case 1, they have given that the space time or the residence time as 1 second and the final outlet concentration as 8 mole per liter. So in the design equation, tau is equal to Ca0 minus Ca by minus Ra. Here 1 is equal to Ca0. So the initial concentration they have given us 10. And here in case 1 the final concentration is 8. So 10 minus 8 by minus Ra. Okay. Now let us find an expression for Ra. So the reaction here is a reversible reaction, A reversibly giving B, and the reaction rate can be expressed as, let's take the forward reaction rate constant as K1 and the backward reaction rate constant as K2. So we can write this reaction rate expression as minus Ra is equal to K1 Ca minus K2 Cb. Okay. Now we know that Ca is 8 mole per liter here. So from this we can find Cb. Cb will be 2 mole per liter. Okay. So how we found out this is, we can find the conversion Xa as 80% from the values of Ca and Ca0. So that means 20% of, sorry, my bad. Yeah. So from Ca, basically we can find the conversion. So Ca is equal to Ca0 into 1 minus Xa. So that means 8 is equal to 10 into 1 minus Xa, and Xa is basically 20%. And Cb will be Ca0 into Xa, and that will be 10 into 0.2, and that is 2 mole per liter. So we found out Ca as well as Cb. Now we just substitute it in the design equation. So design equation is 1 is equal to 10 minus 8 by K1 Ca, which is basically into 8, minus K2 into Cb, which is basically 2. So 1 is equal to 10 minus 8, that is 2 by 8 K1 minus 2 K2. Or we can rearrange this as 8 K1 minus 2 K2 is equal to 2, or 4 K1 minus K2 is equal to 1. So let's take this as our equation 1. Now case 2, we repeat the same thing. Here the residence time is 5 seconds. The final concentration Ca is 5 mole per second, and from this we can find the conversion Xa as 50% or 0.5, and using this we can find Cb as Ca0 into Xa, and that is also 5 mole per liter. So again we write the design equation, tau is equal to Ca0 minus Ca by minus Ra. That means tau, which is 5, is equal to Ca0, that is 10, minus the Ca, final Ca here is 5, by minus Ra, which is K1 Ca minus K2 Cb. We just found out the values for Cb as well. So just substitute it here. 5 is equal to 10 minus 5 by K1 into Ca. Ca is 5, so 5 K1 minus Cb is also 5, so 5 K2. So that is 5 by 5 K1 minus 5 K2. Now if we can cancel out all these 5s here, and this will be 1 by k1 minus k2, which is equal to 5. Now rearrange this. 5k1 minus 5k2 is equal to 1. This will be our equation 2. So now basically we have two equations. The first equation being 4k1 minus k2 is equal to 1, and the second equation being 5k1 minus 5k2 is equal to 1. All we have to do is solve these two equations with two variables and they find the value for k1. So to solve this, what we'll do is, this is equation 1, this is equation 2. So we multiply equation 1 by 5 and subtract this with equation 2. So what we'll get is 15 k1, and the k2s will get cancelled while we do this mathematical solving, and 15 k1 will be equal to 4, or k1 is equal to 4 by 15, which is the forward reaction rate constant, and in terms of decimals k1 will be equal to 0.267. So this is our forward reaction rate constant, and the forward reaction rate constant here is k1, which is 0.267. Yeah. So I hope you guys understood what we did here. Basically what we did is, they were giving us two cases with two different residence times or space times with two different outlet concentrations of A and B. All we did was use those information and generate two equations in terms of K1 and K2. And here in this question, all we needed to find is K1. And if we solve these two equations these equations, 4k1 minus k2 is equal to 1 and 5k1 minus 5k2 equal to 1. If we solve this equation, we can find k1 as 0.267, and that is what we require in this question. Is this clear? Do you want me to repeat this any part of this question? Just you can tell me, I can do it as well. So is this clear? Any doubts? Riyas, Harshal? Do speak up, guys, or like at least type a message so that I know you guys are here. Am I audible? Firstly, did I mute myself? Fine then. We'll stop here, I guess. And yeah, please do respond so that I can know you guys are here, and I can know if you guys need me to repeat any of these things. Fine. So yeah, that's it for today's class, and thank you for joining. Okay. Fine. Yeah, that's it for today's class. And if is this clear? Like, if you want me to repeat any part of this questions, no problem. So if you want me to repeat any of these questions or like any concepts that we learned today, just let me know. Um, Otherwise, yeah, fine. So that is about it for today's class. And yeah, thank you for joining. And do reach me out if you guys need me to solve any particular questions when you are trying to solve these previous gate questions, and we'll look into that questions as well. So we'll continue this, learning of this type of class. So for the first 20 to 30 minutes, we'll learn some concepts. So today we learned half-life and series and parallel reactions. Tomorrow we'll look into some multiple reactions concepts. Not tomorrow, the next class. So we'll look into some of the concepts with regards to multiple reactions. We'll look into the selectivities and yields of different reactions, and we'll see how that is applicable for design equations for ideal reactors. And again, we'll try to solve some problems with respect to these concepts as well. So yeah, thank you for joining, and see you all next week on next week next Monday.